We're going to be doing an advanced motorsports seminar today. But first we're going to show you a few little things about basic TIG welding. We always start our basic motorsports class with basic materials. Basic materials, just plain 1018 steel. This is about 11 gauge steel. It's about 120 thousandths of an inch thick. We're going to be TIG welding this on DC negative polarity using argon gas, a 3/32, 2% serrated tungsten. I'm going to be running about 120 amps, seeing as I have a 120 thousandths thick material. That's the optimum current for 120 thousandths material, 120 amps. I can run that at a higher current if I move faster. I can run it at a lower current if I move slower. The thing about TIG welding is I control all the parameters. I control amperage with my foot pedal, and I control voltage with arc length. The longer my arc length, the higher my voltage. The shorter my arc length, the lower the voltage. I'll control deposition rate by feeding this ER70S2 filler wire into the puddle, and travel speed is controlled by my ability. The faster I travel, the lower my heat input. The slower I travel, the higher my heat input. I kind of started a small TIG weld here, and I used a 1/16 filler. This material is a little bit under 1/8 of an inch thick, and I actually made sure that the top toe of my weld didn't really go up to that top of that plate. I went about 3/4 of the way up, so my leg size is about 3/4 the thickness of my material. Usually that's adequate for full strength weld on a fillet weld. So we're going to shoot for that. Over welding would only cause more heat input and more distortion, and that's one of the big problems with welding sheet metal sometimes. So I'm going to turn this piece over. I'm going to make a weld at 120 amps, and I'm going to travel along at a fairly moderate travel speed. 120 amps is right in the middle of the range I could be running this thickness of material. I have a gas lens, collet body, and a Pyrex cup, so you can kind of see what I'm doing a little bit better with this Pyrex cup. That's about a number 10 cup, so that's a 5/8 inside diameter. Okay, I stopped there, and you can kind of see my heat mark and get a little idea how much heat input was put into that weld. If I turn my current down and run a lower amperage, I can still make that same weld, but it's going to slow my travel speed down some. Okay, so I will turn my current down. I'm going to turn it down on the machine back here, and I'm going to go I went right to 100 amps. I'm going to put the pedal all the way down again and weld at 100 amps. I'm going to travel along as quick as I can at 100 amps, and we'll see which weld is hotter. You can see, even though I lowered my current, my heat input actually went up because I slowed my travel speed down. Volts times amps times 60 divided by travel speed is heat input. Travel speed is a key player. If I turn my amps up to 140, if I can travel quick enough, my heat input will actually go down. So I'll turn it up to 140, and I'm going to travel along as quick as I can. I'm going to maintain a close arc length again. So I kept my arc length close, between a 1/16 and 3/32 from the molten metal. And by traveling pretty fast, my heat input is down probably close to where I was with optimum. My highest heat input was the lowest current. Okay? The reason I show that is I'm going to show you a common mistake. I'm going to go back to optimum, 120 amps for 120 thousandths. I'm going to put it exactly 120, so we're comparing apples with apples. And what I'm going to do now, I'm going to make the common mistake everybody makes. I'm going to carry a very long arc length. When I carry the long arc length, my voltage goes way up, and the area I'm heating is quite a bit bigger. It's like pulling a flashlight away from the floor or the wall. The light gets bigger. So I'm going to heat a bigger area, which means it's going to take longer to melt that bigger area, and my travel speed's going to go way down, and my heat input's going to go way up. I have to really wait a long time. Yeah, I'm going to stop welding. You can see how red that plate is right now. And as I pull my torch away, you can see how big my heat affected zone is, or the area that was heated up. And my shielding, instead of having a shiny weld, my weld is dull. It's because the weld stayed red hot after the argon disappeared. And that's a common mistake I see with steel welding.